Booyah. All right, hearing and the ears here. So we looked at the other part of the inner ear, okay, the semicircular canals and the vestibule, and they are primarily involved with static and dynamic equilibrium. If we go to the other side of this inner ear, now we have the cochlea. And that's what we're going to be spending the vast majority of our time on. There is some anatomy that is crucial to getting that sound wave into the cochlea. So here in this first part, we're going to look at that briefly here and understand and apply the anatomy that we learned prior to coming here and apply it to how we can get sound waves into the cochlea so we can interpret, we can get those sounds and set it to the brain to interpret what the heck is going on here. We do everything within hertz when it comes to sound waves here. You can kind of see the human range there is 20 to 20,000 hertz. Really, the greatest sensitivity, guys, for grins and giggles is anywhere between 1,000 hertz and 4,000 hertz. This is our greatest sensitivity. Okay, so we can acknowledge all of these sounds anywhere between that range, but really in the 1,000 to 4,000 hertz range is where we're going to be. Higher frequencies have higher pitches. Okay. Higher frequencies have higher pitches, and we are going to hear them at a specific spot within the cochlea. Lower frequencies are at another spot in the cochlea. All right, so that's how we can decipher, because the cochlea is hardwired. This region is lower, this region is medial, this medium, this region is more higher pitches. So again, we have all of this hardwired within the cochlea. That's how we can interpret whether it's a high pitch or low pitch type of sound. Intensity, loudness, if you will, that's measured in decibels. Okay. And it's the amplitude. Okay, the amplitude. And it's 0 to 80 decibels there is going to be that range. The higher on the spectrum, the more amplitude, the greater the bombardment, if you will, from those sound waves on those little cochlea hairs and stereocilia. Over time, obviously, that can cause these hairs to be bent a little bit more than they're supposed to. That's going to trigger those little nerves that are extending from those hair cells. And that's going to cause that ringing in the ear. So, if you're going to go to a concert, if hopefully we can go to concerts again, put in that earpiece, okay? Put in those things to help muffle the sound. I've been to a lot of concerts in my day, and the two loudest, I went to, I think, a Motley Crue concert. That was loud as hell. But the loudest one I went to was at the Beaumont. This band called Red. Oh my God. They're like a heavy metal, but they're like a Christian heavy metal band. It's kind of interesting.
I love Red.
Yeah, good stuff. I like a couple of I like one of their albums completely. Like a couple of their songs here and there. But oh my God, I thought my ears were gonna pop. It's the loudest show I've ever been to in my life. And I've been to some crazy stuff. I was at a Slayer concert and I thought my heart was going to come out of my chest. It just was so loud within that building. Motorhead, 3 dudes outside, saw them. Oh my God, some of the loudest sound I've ever heard in my life. But thank God it was outside, so it dissipated out and I didn't have to become too deaf after that concert either. So some crazy stuff, but I digress. Decibels are what we do to measure the loudness, obviously. So we have an outer ear, a middle ear, and the inner ear. And we've already mentioned that, but the outer ear is what's responsible for helping us to funnel those sound waves into the cochlea. We have the auricle or pinna, however you want to call it, doesn't matter to me, it's the same. Okay, helps to capture those sound waves and funnel them into that hairy hole. That is the external auditory meatus. And a meatus, guys, is just a blind-ended tube. That's all that means. Okay. Sometimes it's referred to as an external auditory canal, but canal infers that you can see through through the entire tunnel, basically. And you can't when you are looking into somebody's ear a lot of times. So here we have the external auditory meatus, and that ends at the eardrum, or the tympanic membrane is the fancy pants way to say it. You got ceruminous glands in here too, right? Producing cerumen, earwax, if you will. Helps to lubricate the tube, trap foreign invaders, particles that come in, but helps lubricate that tube and helps sound waves perpetuate through that tube, through this meatus. At the tympanic membrane, that's kind of the line of demarcation between the outer ear and the middle ear. Okay? And the sound waves hit that tympanic membrane. And now we are starting to convert sound waves into mechanical energy. And that mechanical energy is coming from those sound waves hitting that tympanic membrane, causing it to move and vibrate. That moves the malleus, the incus, and the stapes. And that stapes opens right over the oval window. And that stapes opens right over the oval windows, specifically the foot plate of the stapes, if you will, opens up over the oval window. And that's how we get that mechanical energy to now move the fluid within the cochlea, okay, in the scalar vestibule. But this is just an air-filled cavity. This is just an air-filled cavity. There's your 3 auditory ossicles, all right? And they help to transmit and amplify that sound wave towards the cochlea. Stapes is right over the oval window. And as it vibrates a membrane back and forth. And that's what helps to create waves within the endolymph found in, or I'm sorry, the perilymph found within that scalar vestibule there. We do have a couple of muscles, the stapedius muscle, which you can see here. And there's also another one, the tensor tympani, sorry. Both of these are actually working in conjunction with one another. They're both helping to dampen sound, right? It's, there's the stapedius. There's actually controversy between these two stupid muscles. The stapedius muscle is the one that's primarily associated with helping to dampen sound. But as you can see, I mean, the tensor tympani seems to be a lot bigger, comparable. But there is some debate as to who does it more. Who cares? They both do it. It's part of a reflex that helps to dampen sound in the inner ear when you not only hear loud sounds, so that'll pull the stapedius muscle actually will contract and prevent that stapes from oscillating as greatly as it can against the oval window there, moving the fluid and then stimulating the hairs. The tensor tympani, when it contracts, it pulls that malleus away from the eardrum a little bit, which will help to dampen sound. There's some debate as to when each one of them is active. Okay, so when loud sounds, both of them are active. Okay, but when you talk, that causes vibration. When you chew, that causes vibration within this cavity as well. And there's debate as to maybe that's the tensor tympani's job, to be more active when you're doing talking and chewing and whatnot. Who cares? All right. But there is that debate out there. I know you're concerned and want to weigh in probably on message boards. But both of them, the tensor tympani and the stapedius muscles, are both involved in helping to dampen sound. So when sound's really loud, and you have an excessive amount of vibration going on in there, I mean, we're going to trigger some pain receptors. If you've ever listened to something really loud or turned on your headphones and all of a sudden the sound was really loud, it's kind of painful. So there are some pain receptors within here that are going to be triggered as well when decibels become too excessive. It's these two muscles that contract, pulling away from the oval window, pulling away from the tympanic membrane to help dampen sound. Once we go from the pinna, external auditory meatus, tympanic membrane, malleus inca stapes, oval window, ta-da, now we're in the cochlea. We have three chambers: scala vestibule, scala tympanum, and scala media. These have some other names, okay? And it appears that scalas are going to be what they want you to use a little bit more, but there are some other names. This is the vestibular duct. Vestibular duct. Scala means duct. This is the tympanic duct. Because it calls it scala media down here, and then immediately just starts discussing it as the cochlear duct. If you're gonna jump into the pool with scala, then just stick with it, but it doesn't. Okay. So we have an upper chamber, which is what the oval window opens up into, and this is the scala vestibule or the vestibular duct. Okay. We have the chamber at the very bottom. That's the tympanic duct or the scala tympani, and both of these are filled with perilymph. Okay. They are around where the moneymaker is. Okay, that middle chamber, okay, is the scala media or the cochlear duct. Okay, this has the machinery in which to pick up so we can interpret the sounds. And it's filled with endolymph. And remember, this has a heck of a lot of potassium within it. And here you can see all of these right here, all of these on top. I'll put a dot with blue. These are all the scala vestibules. For me, I always remember you look up into the vestibule, okay, to pray. I guess, I don't know. That's what I hear. All right. You tamp things down into the ground. So this is below. Here's the below. So here's my scala tympani. Okay. And right smack dab in the middle is my scala media. And this is the cochlear duct. And it's going to have the spiral organ or the organ of Corti. And there's the tectoral membrane. So all the action is going to be happening inside this little bugger right here. All right. The top and the bottom are connected. Okay. So here, I'll go back. So here's that oval window opening up over the scala vestibule here. Sound waves will travel through this. They don't have to go all the way to the very end. And that's called the helicotrema. Okay. I believe that's, oops, sorry. Okay. This is just that spot where both the two top and the bottom are connected, the two chambers. So if we extend and roll that cochlea out, there you go. Okay. There's the helicotrema. Sound waves can perpetuate all the way down and then, dissipate out through the round window. As you can kind of see, spoilers, okay, sound waves can move the membrane there and travel through the cochlear duct and dissipate out through the scala tympanum and then out the round window. So it doesn't always have to go all the way to the very end of the cochlea, the helicotrema. So this does a nice little fancy job of showing you those parts and pieces moving in conjunction with sound waves. Okay. If I go back here, I have a membrane right here, and I don't know, yeah, they label it right there. Okay. That little membrane right there is called the vestibular membrane. So as the sound waves pass through this vestibular duct, those sound waves will push that vestibular membrane. This is going to now move the fluid within the endolymph, which is going to cause this little thing right here, that tectoral membrane, to start pushing down on hairs, stereocilia. As this pushes down on those hairs, it's actually going to move this bottom membrane, and that's the basilar membrane, which is then going to move the fluid through here, and the sound waves are going to travel out through that round window. And that's what we're trying to show you here. As sound waves enter into the external auditory meatus, and see here they put canal, you can see it's interchangeable, even though meatus is the preferred terminology. So there's my tympanic membrane moving. Moves the malleus, moves the incus, moves the stapes. Again, as that oscillates right over that oval window, that creates waves in the fluid here. And again, as we'll see here in a second, specific hertz frequencies enter in at specific locales. Right? So we're going to have higher frequencies kind of here and lower frequencies traveling down further down the cochlea. So let's just say, who cares? Sound waves enters and dissipates down in through that vestibular membrane. That's going to engage our sensory cells, the organ of Corti, in that cochlear duct. As the sound waves travel through that, they will dissipate out again through that scala tympani. And then the excess sound waves will exit out the round window. So if I was to ask you, describe the path that sound waves travel from out in the environment to be interpreted or to be sensed by the body, say pinna, external auditory meatus, tympanic membrane, malleus incus stapes, scala vestibule, vestibular membrane, cochlear duct, basilar membrane, scala tympanum, out the round window, and done. Scene, end. I haven't decided on, I usually like to ask a question based on describe the anatomy involved with sound, or describe the anatomy involved that helps us to interpret moving to the left. Describe the anatomy involved in helping us to have greatest visual acuity in light or in dark, whatever the case may be. And so, connecting some of the anatomy that we learned prior to here and applying it to some of the physiology concepts, that's a question I like to ask usually. Here we go. Higher frequency, kind of closer here to the base. Lower frequencies travel further down the spiral, okay, further down the cochlea. So those higher frequency sounds, when they enter, so you can kind of see they can enter, whoa. And this is hardwired here to interpret these sounds. these hertz frequencies. Okay. They give it a fancy name. I can't remember the fancy name. I have it a little bit later. Okay. But the cochlea is hardwired, and there's a whole theory behind it. Okay? So it is hardwired to interpret higher frequency, middle frequency, lower frequencies further down. That's just frequencies. Amplitude is something else. Okay. Amplitude, how loud these things are, is going to just trigger more hairs, okay? which helps us to further identify the sound that we're listening to. Loud, soft, certain frequencies. And some of this is learned, right? Okay? We have to be taught what is a high frequency sound. What does that sound like? What's a low frequency sound? And what's that sound like? So some of this is a learned thing, okay? As with all of these senses. Okay? So there is some kind of learned component. So there is some kind of, cerebrum involved there. Okay? Prefrontal cortex, where we understand what it is we're coming in contact with. All right. But the cochlea itself is hardwired. Now, you'll see some numbers on here. I am not concerned with numbers. Okay. I'm not concerned with 3,500. I'm not concerned with 11,000. Right. I put it in there to kind of give you an idea. It's more than just, what they're showing here. Okay. It's more than just a few hair cells. There's a whole heck of a lot of them. Right. And that's all I'm trying to kind of reinforce in here. The organ of Corti, or the spiral organ, the organ of Corti is the sensory component that is allowing us to pick up these sounds. Okay. And it's right there inside that cochlear duct. There is your spiral organ, or organ of Corti. There it is, all nice and close up for you. We have a tectoral membrane. We have various different hair cells. We have outer hair cells and we have inner hair cells. Okay. Extending off of those hair cells are the stereocilia. And there you can see them standing on up. And here you can see them standing on up. Okay. There's your basilar membrane right there. And the vestibular membrane is somewhere up in here. And there's the vestibulocochlear nerve. You can see all these little hairs, all these little hair cells have a little bitty branch that goes to it, and they collectively help us to form the vestibulocochlear nerve, specifically the cochlear branch of the vestibulocochlear nerve. I like specifics, but that is what's going on there. All those little hair cells are embedded in that tectoral membrane. And all it is a gelatinous structure, just like we had when we were interpreting static and dynamic equilibrium. Okay? The macula or the saccula, okay, with the otolithic membrane, okay, or the cupola at the end of the semicircular canals. The hair cells are embedded in this gelatinous membrane. Same thing here. Okay, it's just now we give it another name, the tectoral membrane. All right. We have inner hair cells. We have inner hair cells, more inner, okay, more towards the middle, and outer hair cells further away. Pretty easy. Okay. You can see they're innervated by sensory nerves, and again, this is collectively forming that cochlear branch of the vestibulocochlear nerve. We have outer hair cells. Okay? And as you can see, there's a whole lot of these dudes. All right? These are very interesting. It's the inner hair cells that we generally think of when we think of picking up sound waves, okay? Picking up noises. The outer hair cells help to enhance our ability to hear those sounds. It does this by, it's supplied by a motor nerve. And when they depolarize, they shorten. When the hair cells are hyperpolarized, they will elongate, right? And this has to deal with in what direction the hair cells are going. Are they going towards the smallest hair, the smallest stereocilia, or are they going towards the tallest stereocilia? Okay. This is kind of important. So when sound waves hit these hairs, hit these stereocilia, and start to trigger our perception of the sound, okay, when it depolarizes and they shorten, okay, when they shorten, that's going to help to dampen some of the effect there. When sounds are very light, not as high as in decibel, okay, as the sound waves penetrate down through and start to go into a different direction through the vestibule, through the tympanum, hair cells are going to get bent a different way. And that's going to hyperpolarize this nonsense. Okay? And so we're going to sit there and try to really focus and listen, because these sound waves are going to be much more lower in decibels. They elongate. Okay, so if they elongate, that's going to push these little hairs up into that tectoral membrane there. And that's going to cause this apparatus to bend just a little bit more. So now I can have, well, I did a bad job. Okay. This will start to come down a little bit harder on those hair cells there, so I can pick up very soft, subtle sounds. So it's these outer hair cells that allow us to dampen the effect of loud sounds, or help us to create a greater sense of sensitivity on those inner hair cells if the sound is not very loud. Okay. So they do a couple of great, fantastic things. Here is another picture that shows these stereocilia as well. And again, they have that potassium channel there. Just like we saw in the trying to pick up static and dynamic equilibrium, these channels are always kind of open, and that allows some potassium to come through. So we can be interpreting body position. Same thing here. Right? They're kind of open. As the fluid moves through this cochlear duct, and as that tectoral membrane pushes down on those stereocilia, we either open it more and depolarize it, or bend it a different way and hyperpolarize it. Right? The book talks about all of these stereocilia being connected, and that's what I'm trying to show you here. Okay, they're just protein fibers. Okay, and I'm not going to ask you their name, but here you can see all of these. All of these stereocilia are linked through this. It's called a tip link protein. So when the hair cells get bent towards the stereocilium, it connects them all, and it helps to open up that potassium channel there even more. So even more potassium can come on through. Right? And we release a neurotransmitter, and it's going to be glutamate. Okay, but we release a neurotransmitter, and that helps us to, okay, I hear the TV upstairs. Okay, it's pretty loud. If the stereocilia bend towards the small hair, there's the small one, that creates a hell of a lot of slack. And that really helps to shut the door completely on all of them. And this is going to hyperpolarize. Okay. It's going to hyperpolarize because I have no potassium coming in. Potassium is what causes the release of all those neurotransmitters. Okay, so when we bend towards the small, we hyperpolarize. Bend stereocilia to the small. Okay. When we depolarize, we bend to the tall. Okay. Okay. So again, this is what I just said. When the sound waves enter that scala media, cochlear duct, okay, that tectoral membrane is going to start being pushed down. It's going to start moving, vibrating. Again, because of the fluid being displaced within it. That's going to start bending those stereocilia. Opens those potassium channels. Potassium rushes in, we get depolarization. And glutamate is the neurotransmitter involved. The greater the amount of movement of that tectoral membrane, the greater amount of bending of the stereocilia, the more neurotransmitter gets released, the more greater receptor potential we have. And again, we're going to interpret that as a hell of a lot more louder. Again, where the sound wave penetrates into the scala media is hardwired. And there it is, the place theory of pitch. Okay. The place theory of pitch. Okay. Hair cells closest to where it's coming in are going to be of a certain frequency compared to further down the tube, which are lower. Higher when it first comes in, lower when it lower as it gets further deeper into the cochlea there. Okay. And here I just kind of put the scale on. Again, that 1,000 to 4,000 is going to be where our greatest sensitivity is. All right. So here to there. Okay. But 0.2 is 200 hertz. Okay. 0.1, 100 hertz. This gives us this. Okay. Having higher frequencies at one location, lower frequencies deeper into the cochlea, this gives us the neural coding for our brain to interpret this is a high pitch sound or this is a loud pitch or a high pitch sound or low pitch sound. Okay. It is that neural code that allows us to interpret that. Okay. Again, the outer hair cells are here to magnify. That's it. Okay. Those outer hair cells are there to magnify. All right. Again, depolarizing and hyperpolarizing, making them smaller or making them longer. Okay. If we make them longer, I'm increasing the sensitivity. Okay. These are going to be usually more quieter type sounds. Depending upon which side the sound waves are being more funneled to, allows us to localize that. Okay. So if a sound is coming over here from my left side here, it's obviously, I can pick it up with both, okay? Because if I shut this ear, I can still hear the sound coming to me in my right ear, even though it's not facing it, right? But the sound waves are much more intense coming into this ear than they are this ear, right? So because even though it's the same frequency going into each ear, right, there's a greater intensity, there's a greater amount of sound waves entering this ear than this ear. Okay, again, the sound's coming from that side. So it's going to be hitting this ear a heck of a lot more. And that intensity is what allows me to localize the sound and figure out where it is. Okay. Is it coming from in front of me, straight ahead, to the straight left, straight right, left, back right? Okay. Above my head. Okay. So again, our pinna is going to help funnel that sound waves in. And the intensity at which it's helping us to funnel those sound waves in, if it's facing it, much more intense, and that allows me to localize this nonsense. Okay. I don't know if I wrote it down. To here. Soft sounds. Okay. So those outer hair cells are allowing us to magnify these sounds when they are very soft in nature. From those cochlear branches, they all congregate and leave through the vestibulocochlear nerve, cranial nerve 8. Heads back to that cochlear nerve. It's in the medulla oblongata. Okay. The vestibulocochlear nerve goes back and synapses within the medulla oblongata and pons region there. It also goes to the inferior colliculus. Right? So it goes to a couple major regions right here. The medulla oblongata is going to be responsible for getting it to the inferior colliculus and getting it to the thalamus, which helps me to get it to the temporal lobe. The inferior colliculus in the midbrain is there for really one thing, and that's a reflex. Excuse me. It is a reflex for sound. Superior colliculus is a reflex in the midbrain for vision input. So if something really fast is coming to your head, you move. Inferior colliculus is what does that reflex for sound. As you start to hear something getting closer to your head really fast and you start to hear that, you're going to, duck no matter what, and then, look for it. So the inferior colliculus is a reflex. Middle geniculate body is just where it specifically gets relayed to before it gets relayed to the temporal lobe. I'll probably just expect you to know from vestibulocochlear nerve to the medulla oblongata. From the medulla oblongata, it goes to a couple different locations, the inferior colliculus and the thalamus. And from there, we get to the auditory cortex, which gets us into that temporal lobe. And here you can kind of see, there's the cochlear nucleus, inferior colliculus, middle geniculate body right there within the thalamus. Organ of Corti, vestibulocochlear nerve, medulla oblongata, cochlear nucleus, inferior colliculus within the midbrain, which is a reflex, into the thalamus, which directs it into the auditory cortex. And as you can see in that auditory cortex over there, there are specific little regions within the auditory cortex that are going to be interpreting the various different types of hertz, the low tones or the high pitch tones, okay, and the medium tones, as you can see as well. So there's a huge degree of variation, a huge degree of neural coding within the cochlea as well that corresponds to the auditory cortex within that thalamus. I don't expect you to know where specifically within the auditory cortex where yellow, red, or blue, low, medium, or high tones are interpreted. I don't really care. Knowing where they ultimately end up, yeah, I do. There are some major issues, obviously, with hearing. We have two huge types of deafness issues. One is called conduction deafness, and the other one is called sensorineural deafness. They are two vastly different things. Weber-Bernays test is how you figure out, the difference between to be able to diagnose these two types of things. With conduction deafness, that's easy. I mean, sound waves are just not conducted. Do you have a buildup of wax in your ear? Do you have a middle ear infection? Ruptured eardrum, otosclerosis, presbycusis, old age hearing, okay, which is overgrowth of bone in the middle ear. So there are a number, I mean, these don't sound, ruptured eardrum sounds pretty bad. But I mean, a buildup of earwax, I mean, that can easily be fixed. Otitis media there, middle ear infection, that can be fixed pretty easily. Overgrowth of bone, old age can't be fixed, at least in that regard. Okay? But this is getting in the way or interfering with sound waves traveling through the anatomy. So if it's something that can be easily fixed, sound is just dampened. Okay. Obviously, hearing aids can help with this. Sensory neural deficit or sensory neural deafness. Okay, I've never seen it called perceptive deafness. Impulses are not conducted with the cochlea. So this is a problem with the nerves. Okay. This is because you have been exposed to too loud of sounds. Those hair cells are bent. They are damaged. Okay. And they're producing a constant tinnitus, that ringing in the ear, which interferes with your ability to actually hear sound. So the sensory neural deafness is specifically a cochlea issue. Conduction, I'm just conducting the sound to the cochlea. So it's any number of problems there. Okay, too much earwax, damaged eardrum, middle ear infection, okay, swimmer's ear, old age, all right? All of those are going to interfere with the ability of the body to conduct those sound waves from the outside towards the cochlea. Sensory neural deafness is going to be a specific issue only with the cochlea itself, okay? And I've damaged some part of the organ of Corti. Okay? Usually this is going to be certain frequencies because, sound waves, loud sounds damage only certain types of hairs. So we're going to compare just specific sound frequencies. And you kind of see this a lot in people who work around loud machinery a lot. You'll see a lot of sensory neural deafness. And for this one, they'll need a cochlear implant to help get sound waves to be propagated through so you can hear.
Would you go over the